So with that, we will get started with the advanced Skywarn training. Again, I am Paul Ura. I work at the National Weather Service office in Austin, San Antonio. The pictures here on the front page, in the front image, is that nice, very strong hook echo and tornado on the ground. I'll call this the Salado tornado that happened back in 2022. If you have not taken our basic class before, I really hope you do. But the QR code there on the side, if you do that QR code, you'll actually get our reporting phone number. That is an unlisted number that we ask you to keep very private. Only people that take these sort of trainings in South Central Texas can basically utilize that phone number. That phone number is not utilized in any other Weather Service offices. So if you're watching this outside of our South Central Texas area, that phone number is of no use to you. So you'll need to contact the local National Weather Service office wherever you are located and get their phone number to report. So a little bit of the outline of the presentation. We're going to talk a little bit more about the Storm Prediction Center outlooks. We'll talk about weather models. We will talk about and review severe weather ingredients, mesoanalysis, how the Storm Prediction Center and us kind of have our operations together and how we intertwine. We'll do a little bit of radar interpretation, and we'll talk about our damage surveys. And then finally, we'll kind of wrap up at the very end there. This image here is from March of 2021. This was from Bertram, Texas, which is just west of Georgetown, Texas. A very large supercell thunderstorm came through that particular area. And this is one of those challenging events that I had doing damage surveys, was trying to figure out what damaged this building. It was a very historic building. It was well over 100 years old. So you can't necessarily assume that it was still in good shape and it wasn't going to come down on just some strong wind. I did wind up surveying this as a microburst event and not a tornado, just based off some of the damage that I saw. There was no video. There was not a very good velocity couplet on radar that would indicate any sort of tornado. And the damage was really not very widespread. It was really across only one or two buildings right there. So just judging the way the roof was built and some of the other things I saw, it wound up being a microburst event. Okay, as we dig a little deeper into the Storm Prediction Center outlooks, part of it is trying to understand what the different categories mean and how widespread and the coverage is going to be with thunderstorms once we get into one of those categories. As mentioned in the basic class, our severe weather days here in South Central Texas typically kind of lie in that marginal, slight, and enhanced risk area, which basically means that we'll have isolated to numerous, very strong to severe thunderstorms. And, you know, as far as how intense they will be, they're moderate. We tend to not get anything too crazy when we're kind of in those risk areas. As we kind of step up into the moderate and high level categories, the severe weather becomes much more widespread, and the length of time that severe weather is in effect becomes much more. So longer track tornadoes, much longer and persistent type of supercell thunderstorms. Those moderate and high risk days do not come very often. In fact, the moderate risk that we had, that we'll study here in a second, back in 2022, was the first time we had a moderate risk area in South Central Texas in about 10 years. And the last time that we have had a high risk area in this portion of South Central Texas was back in 2007. So we've gone a very long time without being under a high risk. Let's take a look at the average kind of number of risk days that we have across the United States. It kind of tells a tale of kind of where we have thunderstorms across the United States and where we have a lot of severe thunderstorms. Now, this is just thunderstorm risk. This includes even just garden variety sort of thunderstorms. The least amount are over in California off the West Coast. The water is very cold in the Pacific Ocean, so that does not really allow for a lot of showers and especially thunderstorms to develop. They get a lot of rain events, but as far as thunderstorms and especially severe thunderstorms, just not very many. But as you can see, the Gulf Coast area, in particularly areas of Florida and the coastal areas of Louisiana, they have upwards of almost 200 days that are in a risk of getting a thunderstorm that particular day. So there is a general thunderstorm risk category that the Storm Prediction Center issues, and this is the data that kind of falls out of there. So east of the Rocky Mountains, and especially down by the Gulf Coast, tend to be the most active with thunderstorms. Now, if you want to look about severe thunderstorms, we'll start off at the marginal category on the far left. I'll kind of highlight some of this. So here's the marginal or greater severe risk days. As you can imagine, like we saw with the graphics in the basic course, where a lot of the severe and tornado watches are, the middle part of the country is where we have the most kind of risk days. Literally anywhere between 40 and 50, maybe even up to 60 sort of days per year that are under some sort of marginal or higher severe weather risk day. If you look at just now slight risk and above, so the numbers obviously drop down. Pay attention in these following couple of graphs and graphics of Texas in particularly, and how North Texas to South Texas, there's a very good gradient of the amount of severe weather that we actually get. Here is the enhanced risk, or category 3 or higher, so categories 3, 4, and 5. And again, this is kind of average from 2015 all the way to 2023. Again, in this portion of South Central Texas, what we have are typically anywhere between about 2 and 5 days per year. So it's not very common. And so it's kind of, again, kind of a flag for us to just kind of know that if we're under one of those enhanced or higher risk days, that, you know, we have to staff accordingly. The chances, obviously, of getting pretty significant severe weather is much higher on those particular days. If we look at just moderate risk days and then also high risk days on the far right, you can see that most times, especially with the high risk days on the far right, we basically average less than 1 per year. So, you know, there could be a couple of times where a certain area of Oklahoma or maybe the deep south across Mississippi or Alabama maybe gets a couple of high risk days in a year, but averaged out, it tends to be less than 1. And as far as moderate or so, you can kind of see that, again, areas where you'd assume kind of in Oklahoma and then also the deep south will tend to kind of average more than 1 or about 1 or 2 per year. Again, we don't get that very often, so we're kind of in that less than 1 sort of category. Okay, we're going to kind of show right now what the storm prediction outlooks looked like for our March 21st, 2022 tornado outbreak. We showed some videos in our basic class of some of those tornadoes, and particularly the Round Rock tornado, the Elgin tornado. We talked about the tracks of those. So this is kind of going back now and kind of seeing what was being forecast on that particular outbreak day and leading up to the outbreak day. So we're starting on the far left with day 7. So 7 days before this event, the Storm Prediction Center was already highlighting a very large chunk of Texas for being in a risk of severe weather. So in the springtime, that's not necessarily common, I guess I'll say, but typically if a weather pattern does look like it is developing, very often the Storm Prediction Center will start to highlight that, especially if the models are being very, very consistent. You can see 1 day later, when it was now the day 6 forecast, not much change. It almost looks identical. They trimmed a little bit off from the Rio Grande area. What's impressive is that the percentage of severe weather, the chance of it going up to 30%, was added already by day 5. So that will typically correlate to one of those higher risk areas, either the enhanced or like the moderate or the high. So if you see something out already in day 4 and day 5 that they're already calling for that 30% area, most likely it's going to be more than just a slight risk of severe thunderstorms when it gets to at least day 1. And that's exactly kind of what happened. You can kind of see that by day 3, they added on an enhanced area. They continue to trim off this kind of dry slot or this dry area along the Rio Grande where they were not expecting any thunderstorms to develop at all. Day 2, they kind of brought that back closer to the Rio Grande. They expanded the slight risk area and they expanded the enhanced risk area. And then late morning on day 1 or on March 21st, they updated and they added a moderate risk, or that category 4 that we had into this portion of Texas. Not the whole area, and I'll kind of show you that in a second here, had that, but at least the northern part of South Central Texas, including the Austin area, Georgetown area, Round Rock area, that area was under the moderate risk. I'll go back real quick, especially these day twos, and day twos are updated a couple times per day. The day one is updated, I believe, if I get this correct, I think at least 4 times per day. And so the morning one that came out did not have a moderate risk, but then the one that was issued by early afternoonish time frame went ahead and added in the moderate risk. The Storm Prediction Center also gives probabilistic information, and the way you kind of view this, and I kind of have the definitions there on the right-hand side. The present values of the probability of a tornado within 25 miles of a point. So these are specifically the tornado probabilities. They also have probabilities of wind, and they have probabilities of hail also. The black hatched area means there's a 10% or higher probability of significant severe events within 25 miles of any point. They consider significant tornadoes that are rated EF2 or higher, or significant thunderstorm winds in excess of basically hurricane force, and then hail that's basically larger than golf ball size. So we call that significant severe weather. The other severe weather is your typical, wind gusts of near 60 miles an hour, and your hail that's at least 1 inch in diameter, and maybe your EF0 and EF1 tornadoes. So, the hatched area becomes important, and then those higher probabilities become important too. So, as we kind of watch day by day as the outlooks are issued by the Storm Prediction Center, and maybe we see that, okay, yesterday was just a 5% area, but all of a sudden now it's a 10% area, or now we're in a black hatched area. Those again are flags for us to basically know that, okay, so the ingredients are becoming pretty robust, and we could be expecting some significant severe weather as these probabilities increase. Talking now about weather models. So the model kind of does the math for us. When we go to meteorology school and get our degrees in meteorology, we do a lot of math. We do a lot of calculations. There are a lot of equations that run the atmosphere. Typically, these global models that basically are forecasting weather across the entire Earth are typically run 4 times a day. Typically, the 0Z run and the 12Z run, which are the ones for here in this time zone. 0Z is basically at 7 p.m. this time of year, and then the 12Z run is a 7 a.m. run. They run out a certain distance and a certain time frame. Sometimes those other runs in between don't run as long, which means you don't get as much data from them. The calculations that are made for these weather models around the world, because it's not just the United States that has weather models, it's the Europe and Asia has their own, and the Canadian Weather Service has their own. Some universities have their own. There's a lot of weather models out there. Most of them have to kind of use some supercomputers, which the really good supercomputers are upwards of a quadrillion calculations per second. And so those will run. Sometimes it'll take a couple of hours to run, ingest all the data, let the model do its thing, and before you know it, we have output, which are basically the model solutions. It's the graphics, it's the images, it's the actual temperatures that come out, and that we kind of then base that on as our forecast. Sometimes the models are wrong, and sometimes they're spot on. And the challenge of being a meteorologist is kind of knowing when that is. When are the models being really, really good, and when are they kind of out to lunch? And so some of it is experience. Some of it is you see the output of the model, especially like in 12 hours from now, and you already know that it's wrong just because it's not seeing a lot of the rain, or it's not seeing some of the thunderstorms that are already ongoing. So sometimes you can just use a judgment as to how bad the model is, and if that's the case, then you're not really going to be using that model. Maybe you're just going to be using more what we call nowcasting, looking at the radar, looking at satellite, and kind of seeing where the showers, thunderstorms, maybe even where a storm system kind of travels. But by far, we're used to using weather models. People are used to using weather models and seeing it on TV now. So let's kind of talk about some of these models. I will tell you some of the data that's on the bottom here. I haven't checked this in a while. They constantly update these models, so some of these may be a little bit outdated as far as length of run or the resolution and the different levels that they have. So don't pay too close attention to that. But we have the GFS model, which is the American model, if you want to call it that. The ECMWF, which is the European model, and then also the Canadian model. Those are, I would say, the most common of the long-range global type models that people will basically talk about. You can see that the GFS model on the left there, this one here is basically going all the way out to 384 hours. I believe the European is the one, yeah, the European is the one on the right, and it only goes out to 240 hours. Now, the unfortunate part about social media and getting this stuff on the internet is that a lot of people will post images from that far out, 240 hours, 384 hours. And I'll tell you that posting that kind of stuff is very irresponsible, because many times those models are out to lunch, or there's just no way to even tell the accuracy that far out. And so we only officially forecast out to 7 days in the National Weather Service. There are many folks on TV that will even now start and do a 14-day forecast and even a 20-some day sort of forecast. Again, National Weather Service, and sometimes even day 7 is tricky. So you kind of have to really kind of be careful on looking at this kind of stuff, especially when it gets put on the internet and on Facebook, etc. Another model that we have is called the NAM, and that is run in the United States. There's kind of a global or a larger scale version of it, and then there's a smaller 3-kilometer sort of version of the NAM. You can kind of see that the one on the left has a much bigger kind of area where they have the graphic, and the 3-kilometer NAM is a smaller, higher resolution model, so it has a much smaller area that it is doing. So typically, you know, if you're trying to look at a weather event, let's go back to that March 21st event where, you know, 5 and 6 and 7 days out, we could not use these models right here because they only go out basically 3.5 and 2.5 days. So we're stuck basically using either the GFS, the European, or the Canadian when looking that far out with an event. So, you know, you kind of look at 3 models, and as you get closer and closer to the event, that's where now we can start using the NAM. A good example of the reason why we'd want to use the NAM, especially in winter weather, is those global models like the GFS or the European do very, very poorly with Arctic outbreaks and how cold it will actually be. As the Arctic front gets closer and closer, or we think we're going to get impacted sooner with maybe a big Arctic blast from the north, we'll start to use output from the NAM because it has a much better resolution. It has many more vertical levels than those European and GFS models. And so typically we have a much more accurate surface temperature sort of guess from the NAM when it comes to Arctic air masses. This is just kind of showing, and on a particular date and time, how these different models sometimes will indicate a certain weather event. So this is all looking at a same time, but notice how on the top GFS, the low pressure center is located kind of just southeast of Southern California, and kind of a little bit tightly kind of wound with the ISO heights here. The Canadian model is much more stretched out, going down toward the southwest. And you can see the European model is much faster. At the same time frame, it has it well east of California and actually across Texas. So many times when we're trying to compare the models, we will look for run-to-run consistency. We will look to see how it is initiated, and we'll look at the strength of the system. All those things come into play on whether or not are we giving a 20 or 30% chance of rain, or maybe we don't have any chance of rain at all because we think that, well, we're going to go with the slower speed of the GFS and the Canadian model. We think the European model is maybe way too fast. So those are day-to-day conversations that we have amongst ourselves as meteorologists inside our operations area when we're trying to talk and compare forecasts with surrounding offices. That's what we have to do. We have to kind of compare and kind of see where the consistency has been. Maybe yesterday the European model was much slower, just like the Canadian and GFS, but all of a sudden the newest run has it much, much quicker. A little bit of a red flag for us if all of a sudden it was on a certain trend and all of a sudden it's now changing. Now, if it looks like it's the same speed tomorrow And then also the next day or the 12 hours with the next model run. Well, okay, well maybe, geez, maybe the GFS and Canadian are now catching up in speed to what the European is saying. Okay, well now all the models are maybe kind of narrowing in on a consistent timing. Well, then maybe that's when we'll kind of change our forecast or maybe adapt it a little bit. So here's just kind of comparing runs to runs. The way you kind of read this slide is start down here in the bottom right, okay? So this was a forecast 150 hours out, okay? Then, so you can kind of see where this trough, where this black dotted line is kind of across Texas like this. And you can kind of see how the trough was kind of angled down into maybe deep South Texas. This same time frame, the next day, which has now become a 132-hour forecast, kind of has the same troughing over the East Coast, this dotted black line, but now it kind of heads more almost due west across mainly West Texas. So kind of a much weaker looking sort of trough. If you now look at a 108-hour forecast, it's now a little bit back to being a little bit stronger of a trough, kind of moving through Texas. And then finally, the 184-hour forecast, okay, it looks pretty consistent now from the last model run that we had. So overall, the timing and the way it looks isn't bad. This 132-hour forecast kind of looks a little squirrely in there, but for the most part, it's comparing pretty well, and from run to run, it looks pretty decent with the timing and the positioning of where that trough axis will be over Texas. As we get closer to an event, or as we get into that, like, let's say the day of a weather event, or even maybe the next day, that's when we'll be able to kind of start using a different set of models. We can still use the GFS and we can still use the European, those global models, but there's some much higher resolution models now available to us. They're called convective allowing models, or what we call CAMs. They can resolve individual storms. Now, you have to, again, use that with a grain of salt, because models pegging exactly where a thunderstorm will form 24 hours out most likely is going to be wrong. But you could use that as a regional sort of forecast, where if they show, let's say, a couple of models, tomorrow afternoon are showing a couple of thunderstorms popping up in our Texas Hill Country, I wouldn't necessarily call one of those particular emergency managers in that particular county and say, hey, yeah, by the way, between 2 and 3 o'clock tomorrow, there's a thunderstorm that's going to form. We're not that good. But we can typically make a pretty good statement that, yeah, somewhere out in the Hill Country tomorrow afternoon, maybe between noon and 5 p.m., we're expecting possibly some pop-up thunderstorms to form. We can either use these models individually, or we can actually use them together in what we call an ensemble. When we have many different models and you kind of compare all of those outputs together, we call that an ensemble. And many times these CAM models also have simulated radar. So the image up here is a good example of this. This is one of our CAM models called the HRRR. And what you're seeing on the screen is actually a radar depiction. This is a forecast of what it thinks the radar will look like at a certain time. Again, it doesn't mean that it's actually going to look like this, because again, we're not that good yet. But the models are depicting where it thinks the rain will be, where the heaviest cells will be at a certain time. There are some days where, surprisingly, these models are very accurate, especially when it comes to line of thunderstorms and so forth. It becomes a little bit more iffy when you're talking about those individual thunderstorms and where they're actually going to pop up. Again, two examples of these CAM models are the HRRR, or we call it the HRR model. It goes out typically 18 hours, run every hour. However, every 6 hours, there's actually a 36-hour sort of run. So you can't really see until tomorrow, but only about 4 times a day you can see a couple of days out, or about a day and a half out. So again, you're limited. You're limited within today and tomorrow, basically seeing what these models are doing. And a pretty darn high resolution, where its resolution is down to about 2 miles. Another different CAM model is something that they actually run out of the Texas Tech University. They have a meteorology program there where you can get a master's and PhD in atmospheric sciences. And so they run their own model out there. And a lot of times that output is available on the internet as well. I can't remember if they actually have that available or you have to have a password to that. I'll have to check up on that. But for the most part, those are a couple of different CAMs that we have out there. The Storm Prediction Center has something called the HREF. And the HREF is kind of a combination of a bunch of different CAM models. Down in bold here, you'll see it's made up of the HER, the ARW, the NMM, the Nestle-Whorf, the NAM-NEST, and also previous runs of all of these models. So it is run to between 30 and 48 hours. And again, so it's a combination of a bunch of models all kind of outputting something on paper, if you will, that we can basically see. So they have a great website, the SPC does, where you can look at these and you can look at them individually, or you can kind of look at them just as the HREF overall. So you can look at the whole thing, or you can look at them all individually. Other examples of model ensembles. So the GFS model, the American model that goes all the way out to 384 hours. It is run multiple times using small little, what we call perturbations, or small little changes in the model. And so then what you get is one model that's run multiple times with basically different outputs. And so that is called the GFS ensemble, or the GEFS. That is very handy in kind of looking to see possibly what the operational GFS model is saying. So on this image on the far left here, this solid black line, pretty sure that's the operational, it's either the operational or the mean, I forget which one that is. All these little gray lines are all individual runs within the GEFS ensemble. So the GFS is run all these multiple times, and these are all the different outputs of how much rain may fall. Overall, the highest here is about 2.4 inches. This is for Austin on a particular day, back last February. The minimum is basically just above maybe 1/10 of an inch. So all these lines represent not only a mean, the operational one, but then also all the possibilities. So if they're clustered together, that's pretty high confidence. If they're spread out like this, there's a wide range of possibilities, and maybe our confidence is not very high as far as how much rain Austin will actually get. Now, our confidence should be there that basically sometime within the looks like the 7th and 8th of February, there's probably going to be some rain, but actual amounts are going to be much harder to kind of determine. You can also look at this kind of graphic here on the far right is a certain height level of pressure. So when we look at weather and we look at pressure heights, 500 millibars is a very common one. And so you can actually kind of see also with all the GEFS and all the GFS runs, what maybe the upper levels look like. And just like when you're much watching the hurricanes and you see those spaghetti plots, right? When all the lines are together, again, that's high confidence. When the lines look like this, where the lines are literally spread out all over the United States, that is very low confidence that we're not sure exactly what the upper levels will look like. In fact, this is a 336-hour forecast. So way out there. And it just shows you that all the different model runs of the GFS show multiple different sort of scenarios. So again, that's another prime reason why we typically do not go out that far with actual forecasting, just because the models are flip-flopping kind of all over the place for what they want to do. We have some great ways of kind of comparing models. All these different colored plots are temperature, 2-meter high temperature. So basically surface is what we kind of use as surface temperature. And you can see early on in the forecast here in January, all the models were very clustered up, all of them, all within about 5 degrees of each other. And then as we get out in time, so here's Monday and then Tuesday and Wednesday and Thursday and Friday and Saturday. So you're talking about nearly a week later, some models are showing that it's going to be 20 degrees and other models are showing it's going to be 50 degrees. Okay, that's a pretty big spread. So again, at this point, if we're doing a forecast for day 6 and day 7, gosh, there's a spread here even of nearly 30 degrees of what maybe the temperature may be in the morning time. And in the afternoon, the same thing. We may be below freezing for temperatures in here, or we may be in the 50s or 60s. So again, that's a very low confidence kind of forecast if you see the spread this far apart with all the different lines and all the different weather models. We get assistance by model soundings. Of course, soundings are created by weather balloons typically, and they launch them around the world. There's about 1,000 sites around the world that launch weather balloons daily, actually twice a day. But the models can also depict what a sounding will look like. And basically a sounding is a plot and a trace of the temperature as you go up into the atmosphere, as well as the dew point temperature. So you can see where moisture levels are, you can see where the temperatures are very cold or colder than average. You can see them where they're higher or warmer than average. And that is very important for us meteorologists to kind of know how unstable the atmosphere is, possibly even what the conditions would be for severe thunderstorms. All of that are kind of figured out from our soundings, from our weather balloons. So of course, the models can replicate that, what the sounding would look like on an hourly kind of sort of basis. So it kind of fills in all the gaps between all the observations is what the models can do. Again, it's just a model depiction though. The upper air soundings that we actually get from the weather balloons are actual data. And that's where a lot of the starting point is of those weather models. You can also do two-dimensional slices in the atmosphere. You can look at cross sections of humidity and wind and cloud cover and moisture and just about anything that we want to look at, we can look at cross sections. I look at that very, very often, especially when I'm doing aviation forecasting and I'm trying to figure out where maybe the cloud decks will set up, maybe how windy it will be, maybe even when a trough axis is going to come through an area, are all that you can basically depict through a cross section like that. And even websites like Tropical Tidbits up here, it's just a public website. I've got a couple of, the next slide will actually show a couple of these different websites where you can go to get this information. There's a lot of public data out there where you can look at all these weather models. This is just a screen capture of 3 of them. Pivotal Weather, Tropical Tidbits, and the College of DuPage are ones that I guess are favorites out there. They have some pretty good depiction on them, pretty easy to navigate, pick which model runs you want, all of that. So those are kind of the ones that I look at sometimes when I'm at the house. So that kind of ends that little section of our training. We're going to kind of dive a little bit now more into the severe weather aspect of thunderstorms and talk a little bit more about wind shear. If you remember back in our basic training, the wind shear is the increase of wind with height. And that is a very important ingredient because it takes our normal thunderstorms that typically are vertical up and down, and that strong wind aloft will actually tilt them over. A lot of times will then blow the hail and the wind, the wind, let's start over again. The wind will blow the raindrops and the hailstones out of the updraft and will blow it pretty far downwind, maybe miles downwind. That separates what the updraft and downdraft are, and that creates kind of a perfect engine where the severe storms can then last hours and hours. One thing that we will look for on the soundings and even the model depicted soundings are the moisture content. We call this precipitable water. It's basically vertically, it's kind of stacking up all the moisture in the atmosphere and vertically kind of representing it. In this particular model that you see in the sounding up here, it says PW equals 1.7 inches. That's a good total. I will tell you that during the middle of the summer, where maybe we have a lot of tropical atmosphere coming in into Texas, that could be well over 2 inches as precipitable water. That will give us a clue, basically, how heavy the rainfall could be. So a lot of our flooding events that we get, we have high precipitable waters. That means that basically the atmosphere has a lot of moisture in it. And so when those thunderstorms tap into that moisture, you can get a lot of that coming down to the ground. We can view these soundings a lot of times and compare it to climatology. So a good example would be maybe in the wintertime, where our typical precipitable water value is well under 1 inch. But the sounding was launched in Corpus Christi or out in Del Rio, Texas, or the models are depicting, 1.5 inches of precipitable water in the middle of the winter. We could go back and look in climatology to see how often that has occurred and how rare that is. Obviously, if it's extremely rare, or it's a very low precipitation or low kind of chance sort of event, we know that, okay, well, if some rain happens, we could be dealing with maybe a wintertime sort of flood event, just based off, this is something that we just normally don't see very often. Now let's talk about instability again. Again, this is one of our ingredients, but let's dive a little bit more into what it is. So the air in the atmosphere typically gets colder as you go up. Very common. So, when you're talking about 30 and 40,000 feet up where the airplanes fly, it's very common to be minus 40, minus 50 degrees up there. It's warmest down at the surface, coldest as you head toward outer space. What that will do, that will allow a parcel of air to basically freely rise. Think of a hot air balloon, okay? It'll freely rise up there. You'll get the big puffy clouds and everything else that kind of happens when you have an unstable sort of atmosphere that's typically set up with warm air at the ground and cold air aloft. You can, however, sometimes even have a warmer layer of air that sets up in the mid-levels. Talking anywhere maybe between 4,000 to 7,000 feet up is a much warmer segment of air. And what that does, that actually creates what we call an inversion or a cap in the atmosphere. Imagine kind of a Tupperware, right? And you have a lid on the Tupperware and you forget to pop it or vent it when you put it in the microwave to warm up your leftovers. In about a minute or two, once it's really warmed up, all of a sudden you hear that pop and that bang and that mess that has just occurred in the microwave because it basically exploded. And so what will happen on some of our really, really good severe weather days is that we will have this cap or this inversion, which will bottle up all of the energy in the lowest several thousand feet until finally the cap is broken. That lid is broken, and then you'll have explosive development actually with the thunderstorm. So all of this kind of comes in play. Some of this we'll know by the weather model. Sometimes it'll be known by actually launching the weather balloons and seeing how strong that inversion or that cap actually is. A way to measure the instability of the atmosphere is by something called CAPE, convective available potential energy. So it is the potential energy that the atmosphere is holding. When we have a sounding, one of the numbers that is created by the sounding that we see on a graphic is how much potential energy this area is in blue. The bigger the potential energy, the larger the thunderstorm can be, or the more severe the thunderstorm can be, or the bigger the hail can actually kind of be. So it's a good indication of how fast the updraft will be in that particular thunderstorm. So as the weather balloons and the aircraft measure the temperature and dew point vertically in the atmosphere, that is where this CAPE computation is actually coming from. So these are a couple different soundings that we had. This one is out in Del Rio on the far left, DRT, and Corpus Christi here. And so these are kind of the mapped out areas of CAPE, or again, that potential energy. You can see that this area is kind of a smaller area in Del Rio compared to the Corpus area. And in fact, this CAPE here is a little over 2,000 joules per kilogram. And this CAPE amount here in Corpus Christi is well over 4,000 joules per kilogram. So according just to the numbers, the thunderstorms would have bigger potential in the Corpus area as opposed to the Del Rio area. There's other factors that can come into play, wind shear and some other things, but just based off that, we could expect some bigger updrafts over the Corpus area than maybe the Del Rio area. Now again, this is just potential. There are days along the Texas coast and in Texas where every day we have 4,000 and 5,000 joules per kilogram available potential energy, but yet we don't have a drop of rain that happens because then the atmosphere is very unstable, but there's nothing to tap into it. There's nothing to actually cause a thunderstorm. And that's where you need the lifting mechanism. So this is how we can actually tap into all of that CAPE or that moisture and break the inversion and actually get a severe thunderstorm to actually form. It can be, the lifting can come from a cold front moving through. It could be a bigger cyclone or a low pressure center with the cold front and the low pressure center and the warm front, what you call basically a storm system coming across the United States. It can be an upper level disturbance or a trough in the jet stream coming across. We could have just daytime heating, what we call differential heating. Many times, if in an area of the United States, Florida is very common, where it's just hot and humid. Well, in a certain time of day, about maybe 2 or 3 or 4 o'clock in the afternoon, it gets so hot that that causes those parcels of air to rise, breaking through the inversion, and all of a sudden you get a thunderstorm to form. There was no cold front. There was no upper level disturbance coming across. It was literally just what we call daytime heating. And so sometimes daytime heating can pop those thunderstorms, again, mid to late afternoon hours. We could have a dry line coming across. That is a boundary between very, very hot, dry air in West Texas versus the very warm and humid air of East Texas. It's like a front, if you will. And then also you could have literally orographic lifting. If you have air that is getting pushed up into the mountains of West Texas or into our hill country of South Central Texas, that may be just enough lift to break through that cap and to actually cause showers and thunderstorms to actually form. Talking a little bit more about wind shear. Again, that's the differences of wind speed with height. Now, what we didn't explain in the basic class is that not only can you have speed differences as you go up, you can also have directional differences as you go up. So if we just have 10-mile-per-hour winds at the surface and 40-mile-per-hour winds at 10,000 feet and 100-mile-per-hour winds at 30,000 feet, that is speed shear, okay? But what if you have winds near the ground at the southeast, and maybe a couple thousand feet up, those winds turn to the southwest, and then maybe at 10,000 feet, they're due westerly. Now we have directional shear also. So wind shear is not needed for actually storms to develop, but the higher values of wind shear will make that storm last longer. And we talked about that in the basic class. When you don't have a lot of wind shear, you have simple thunderstorms that die off in an hour. As you have stronger levels of wind shear and stronger numbers of wind shear, that's when you'll actually have the very organized thunderstorms that will last hours and hours because you've created a perfect engine with a fuel area and an exhaust area, if you recall that. The directional shear comes into play, especially when we're talking about potential for tornadoes and potential of what kind of thunderstorm we're actually going to get. Are we going to get splitting supercells? Are we going to just get normal thunderstorms that become supercells? Again, you can have a lot of speed shear and you can get a lot of really big severe thunderstorms that produce a lot of hail. But a lot of times, if you don't have that directional part of it, the actual tornado threat will be much lower. So we do look for that directional shear, especially when it comes to tornado potential. Let's dive a little bit into the radar and the radar products that we issue. The most common that you actually see on apps, on TV, is called the reflectivity. We'll talk about that next. We typically have velocity products. We'll talk about spectrum width. We'll talk mainly about reflectivity and velocity and show those sort of images in our kind of segment of going through a couple of the tornadoes. I'll mention spectrum width, differential reflectivity, correlation coefficient, and also specific differential phase. Spectrum width is a really good way to determine turbulence. So as an example, if we think we may have a tornado on the ground, in this case, looking at the velocity couplet here, if there's a lot of turbulence near that velocity couplet, maybe that increases our confidence that that may be a tornado on the ground. When we look at differential reflectivity, this is one of the products from dual polarization, as well as correlation coefficient and specific differential phase. Differential reflectivity is a product where we compare the vertical kind of beam that goes out when we talk about our dual pole. It's a beam of energy that goes out on a vertical plane, and then we send out a pulse of energy on the horizontal plane. And the difference of those is what we call differential reflectivity. What that means to us is that at certain numbers, we will be thinking that we are seeing more of just rainfall versus maybe something that is not so squatty. If you didn't know this, as a raindrop falls, it gets squatty like a hamburger bun. It is not a perfect circular raindrop. The very, very small drizzle drops are nearly spherical. But as a raindrop gets bigger, it gets squatty, much like a hamburger bun, which means that it has a much larger horizontal sort of look as opposed to a vertical. So again, we kind of use differential reflectivity to kind of pick out where we think we are getting raindrops versus maybe something else that's more spherical. The correlation coefficient is used to kind of see, okay, everything that's falling from the thunderstorm or from the atmosphere, is it kind of all the same shape? And if it's kind of all the same shape, then it's all kind of one color, typically this deeper purple color. If there is things that are falling of much different shape, then it becomes a little bit more chaotic, kind of like almost what you see with these greens and the yellows and the blues all kind of mixed together. Correlation coefficient can be used to actually find debris from a possible tornado, and we'll have a slide on that called the tornadic debris signature. And then finally, specific differential phase is a product that we use sometimes to really figure out where the heaviest rain or the heaviest rain rates may actually be. So let's talk a little bit in depth about reflectivity. Again, this is a pulse of energy that goes out from our radar. It will then reflect back with what is hitting, okay? So if there's very, very small objects out there, then it'll come back with very little what we call dBz. That's the reflection sort of power that we measure. So in the case down here, it is showing rain is sending back maybe 30 dBz. That will maybe kind of colorize as, let's say, the darker green colors or maybe some of this yellow. That would be 30 dBz. Higher up in the atmosphere, larger hailstones have a much larger sort of look to them, cross section for them. So that will reflect back a larger amount of power, maybe 60 dBz. That may show up maybe as the darker red, maybe even the purple out there. And then finally, even up at the higher portions of the thunderstorm, the numbers kind of drop off again, maybe to 25 dBz. So what we're seeing on the apps and what you're seeing on most of the radar screens where we're showing thunderstorms is this lowest level of return. We, as meteorologists, when we're investigating a thunderstorm and looking at the 3 dimensions of it, we are very curious as to what's happening in the mid levels of the thunderstorm. Now, some apps you can actually pan up and you can see the higher elevations. There's also a product called composite reflectivity, and what it will show is the highest reflectivity at any level. And so the composite reflectivity product is kind of a good way to see, well, where is it possibly going to be hailing, because basically it would be showing that 60 dBz as opposed to the 30 dBz. So that's just kind of a rundown a little bit on that. When I talked about correlation coefficient and also some of those other products that we had, those come from dual polarization. And again, this kind of shows you that there is a variance. One pulse that goes out is on a vertical plane, and the next pulse that goes out is on a horizontal plane. So it does create more of a cross section. This little rain kind of shows you that hamburger bun sort of look. A very, very small drop of 3 millimeters will be nearly spherical, but a bigger raindrop has that hamburger look, which means it has a much higher horizontal look than a vertical. Hailstones tend to be more spherical, so they'll be more even with the horizontal pulse and the vertical pulse. And then, of course, we have things that are flying through the atmosphere like bugs and birds and bats and other things that have a very chaotic sort of look to it. So we can use that dual polarization to kind of find out where we call them biologicals are actually occurring. And again, a lot of that is because it's very chaotic when the power is returned back to the radar. It won't be all of the same. And so we'll be able to kind of pick out those biologicals that way using dual polarization. Here's a good example of how we use correlation coefficient. And again, are all the objects the same shape, or is there different stuff out there? So when we use it in combination with reflectivity, and in particularly with our velocity products where we see a couplet of wind coming toward the radar and wind going away from the radar. So cool colors are typically toward the radar. So in this case, it'd be coming toward the radar. Or maybe if the radar is up there, I don't know which direction it is. Most likely it's going to be, let's see, counterclockwise. So it would be up here. So cool toward the radar, and then red away from the radar. So a counterclockwise spin there. So that would be a possible tornado on the ground. Now, if we're seeing this, the drop off or the low numbers of correlation coefficient right where we're having this couplet of velocity, that is nearly a 100% indication that we have a tornado on the ground, because what it is doing is it is seeing all this debris. And so especially at nighttime when storm spotting is very difficult and we can't get a lot of visual to tornadoes, except maybe some power flashes or something would be a potential there. This kind of allows us to know that it's probably tossing up into the atmosphere, sometimes several thousand feet and sometimes tens of thousands of feet up into the air. We know it could be a very powerful tornado on the ground if we have debris going all the way up to 10 or 20,000 feet. That's called a tornadic debris signature. So let's kind of review some of what happened on March 21st. This was the tornado outbreak. You can see all these several supercells all form off somewhere between basically 3 and 5 p.m. At one time, I believe we had 3 EF2 tornadoes on the ground, like within a 10-minute period. So very rare for us. This is something that you'd much rather see like along a dry line up in Kansas and Oklahoma during one of those big severe weather outbreaks. Well, it happened over us on this particular day. So I think the first one we're going to actually look at is this particular supercell that technically formed down here just south and east of San Antonio, but then moved up toward the Seguin area right along Interstate 10. So on the far left here, we have the reflectivity. You can kind of see the hook that develops. Down below here, we have the correlation coefficient. And up here, we actually have the velocities. And so right around here is where the tornado actually touched ground. It didn't touch ground right on Interstate 10, but just off to the side of it, and was on the ground. Luckily, we did not have any fatalities with this one, but there was some cool afterward sort of video. This is from DPS helicopter that was actually going through and documenting a lot of the damage that all these different buildings kind of got hit with. So it was quite fascinating to kind of be able to use this. The importance of being able to use drones now, helicopter footage, is that, you know, on these private roads, on these private properties, on these ranches, many times we as the National Weather Service, we do not have access to any of this sort of video, or we can't see it from the ground level. And so that's where aerial kind of photography is really superior for this. You can also see how widespread the kind of damage pattern is on some of that. And that also kind of just shows you to the strength of the tornado, and also kind of proves that it was probably a tornado. If a microburst would have come in here, like we talked about in the basic classes, you know, the roof would be off in one big piece, maybe something like that. Here, it was destroyed, and the pieces of the roof are pretty much kind of everywhere. This was actually the damage survey that we did. Some of it was based off ground, but a lot of it was based off the helicopter video and seeing exactly kind of where it was. So it started down here, just basically north of Interstate 10, and crossed just kind of to the northwest of Luling. It did cross Highway 90 here. We did rate this as an EF2 with peak winds of 115 miles an hour. It was on the ground for about 7.5 miles from what we could tell. So we called this the Kingsbury tornado. A couple of other tornadoes that occurred was a tornado up in Gerald. Gerald, of course, has been hit multiple times with tornadoes, most historically the 1997 EF5 tornado that killed well over 20 people. On this particular day, there was a smaller tornado that formed just west of town that did move north to northeast. And it was on the ground for 9.3 miles and peak winds of 100 miles per hour. The biggest tornado of the day, or the longest track tornado, was this one that we call the Round Rock tornado. Started down here right near the I-35 and I-45 interchange right at Round Rock. Literally crossed that interchange, went right through a parking lot of a Home Depot and a Walmart, and then continued all the way up until it actually crossed right near the Granger radar, about a quarter mile away from the Granger radar, and then eventually made it and dissipated finally into Bell County. It was rated as an EF2 tornado with peak winds of 135 miles an hour and a path length just in our county of 29 miles. If you add on this other path, it was well over a 30-mile long path tornado. 16 injuries, luckily no fatalities. What was useful on this particular damage survey was that there were so many homes damaged, hundreds of them. I was not going to be able to make or our workers at our office, not going to be able to take a picture of every house, make sure that we visited every street and so forth. And so right now, when you have a pretty big disaster in Texas, the state of Texas will actually send out with a QR code. The local cities and counties will advertise it, and you can basically self-report. You can take pictures and you can plot it on a map. Basically what happens when you upload your image up to the state, it will plot. What you see on this map are all the dots where citizens actually uploaded images of their damage at the houses. Well, I was able, with the state's permission, go in, look at the damage photos, and I was able then to totally distinct where the path of the tornado was and the width of the tornado damage based off the self-reporting images. Much more accurate than what I would have been able to do on the ground and just zigzagging back and forth with streets. That would have taken me well over a week to be able to do all that. Plus, you want to also see the damage before people clean up, because sometimes that damage are actually clues of what's going on. These are some of the drone footages that we got from the Round Rock. This was an interesting aspect of what happened to this kind of large warehouse. This is all made out of concrete walls and everything. So it was kind of interesting trying to figure out what happened here. A lot of these trees are fine. The tornado came from this direction. So how is it that this warehouse had such substantial damage, but yet all of these trees are kind of untouched right here? A theory that I came up with was that these garage doors right here got busted in, or there was a failure of this particular concrete wall. And once air and wind got trapped into this warehouse, it popped the roof. You can almost kind of see here where the roof panels are laying outward, like the whole thing busted up through the roof. That happens very often through houses too. If I may or may, I don't think I have a picture of it. There were a couple of houses where the garage doors failed and wind got into the garage and the roof right above the garage got popped off. That happens a lot actually during hurricane situations. So it could be that a couple of these doors failed and the wind of the tornado actually got forced into the warehouse, and the pressures and just the increase of wind in there popped the roof, and that's how you have all this damage on top of the warehouse. This is a before and after image. This here was a house, and this was like a pool house here. This is in Round Rock. So there was right here, and you can see the entire roof was actually pushed off and blown that way. The long arrow here is the track of the tornado of how it crossed. So you can see all the 2x4s from all the other damage from all the other homes. So this becomes very, very useful again when trying to determine tornado path, which direction was it coming from, which direction was it moving. All of that is very, very helpful before and after images. A couple of other images showing roof damage. You know, typically when I go out and do damage surveys, some of what I'm actually looking at is how much of the roof is gone. Well-built houses on foundations, built properly. When I see sections of roof left off, that's kind of more into that EF1 range of a tornado. If you see the entire roof off a building, that typically pushes it more toward that EF2 sort of look. This was images from the Walmart parking lot of the tornado actually crossing right through. So it's only been on the ground for about a minute or two. This is right at the I-35 and I-45 tollway interchange. Moving very, very quickly. This was not a slow moving tornado. It actually moved very, very quickly. So you can see the danger here. Everybody, I'm gonna play it again actually so you can see it. People running through the parking lot, not staying in their cars. I mean, it's a little crazy how people put themselves in danger like that. Even people taking this video, you're outside with all that flying debris and everything else. When I drove through that parking lot, I remember the one, it's like an oil change place, had a 2x4 stuck through its sign, kind of skewered through that. These were images taken from the parking lot of that shopping center. On the far left, cars overturned, a bank was damaged, a restaurant was damaged. On the far right is some pretty significant high-end EF1 damage that we had. At one of these homes, I think I rated it again as maybe an EF2, I can't remember. But you can kind of see the devastation to the roof, the lumber, the timber everywhere, the nails everywhere. It's just a really big mess when a tornado hits an area like this. Kind of opposite of that is if a microburst would have come through here, again, everything would have been in big pieces and not literally shredded up like this. That's kind of those visual clues that I wind up kind of looking at. And then a couple of other tornadoes that happened that day. An Elgin tornado happened near Weberville and crossed just to the southeast of the town of Elgin. And then also a smaller tornado, also an EF1 down here by Giddings, Texas. This Elgin tornado had some pretty famous video with it. This was the video of the pickup truck, the red famous pickup truck, where a teenager was driving it and it got flipped over right there in the middle of the screen. He got upright and then he continued to drive away. He did actually get a new pickup truck out of the deal. A dealership up in Dallas, Fort Worth, I believe, saw the video and actually got him a brand new pickup truck like that. So he survived it. Very, very lucky, going right through a tornado. This was one of the tornadoes as well. This was drone footage. One of the storm chasers that was chasing this day around our region provided some great drone footage. Interestingly enough, not a large funnel with this. The funnel was nearly invisible, but obviously you can see all the damage. Look at, so this is the house. That was a mobile home that was destroyed down the bottom right. This is about a house that is about to get hit. And you can see the roof gets peeled off and then all the insulation gets sucked out. Look at the vortex over here, kind of rotating around. So this was kind of almost like what we call a multi-vortex tornado. There appear to be a couple of vortexes rotating around a main column, but you can see the mess that it causes. A lot of debris all over the place. Wrapping it up, we are going to talk about a tornado that happened then just a few weeks later. Started around Florence, which is in far northwestern portion of Williamson County, crossed the Bell County line, and was headed right towards Salado on I-35. So this happened on April 12th, 2022. Will Leverett, one of our storm spotters and someone that provides us with great photography, gave us permission to use some video that he took. And so what I did is I went back and compared what the video was showing versus what the radar was showing at the exact times based off the video timing. So when it started out in Florence, there was a little bit of damage out there. Couldn't find a ton, but there were some big oak trees that were uprooted. Here's a good picture of one in somebody's property. Again, it kind of started off to the far west. We listed this as an EF1 tornado. For much of its time, it was an EF0. But right as it kind of got to the county line and we crossed into Bell County is where it strengthened pretty significantly into an EF2, which will kind of show that. This was the Bell tornado. And so this is the video that we're going to show. You can kind of see it came across the Bell County line and was continuing towards Salado in I-35. And that was going to be bad, very, very bad. And then luckily the tornado started to weaken and then took a hard left turn and then finally dissipated up here by the lake. This wound up being a very high-end EF3 tornado with peak winds of 165 miles an hour. There were 23 injuries, but no deaths, luckily. This was when I actually crossed the county line and I looked at some of the damage at this location, and it was the strongest tornado damage I've seen in my careers, and so it was quite impressive. Looked like a bomb had gone off. Trees were just shredded, and there just wasn't much left of pretty much anything. So this is just going to be kind of from beginning to end, the entire loop, and then I'll go back frame by frame and kind of show you what was kind of going on. So again, it's going to start down here. It gets its first kind of baby, I'll call it a baby hook. If you look at velocities, this is where it really gets strong. And this is where it has actually a very large tornadic debris signature. But, and then you can kind of see it kind of veer off to the left. So pay attention, again, we'll let it go. Pay attention to the velocities up here. Okay, there's a couplet, so there's the red and green. And so you can basically track the tornado where my cursor is. And then as it was going towards Salado, it then turned. And then it went almost due left and then it eventually dissipated. As they change direction like that, tornadoes, that is typically on their weakening phase. And so typically very soon after it makes a hard left turn or right turn like that, you'll see it dissipated, or a lot of times what happens, the storms will actually cycle through and a new tornado is actually forming. We've had several incidents like that in our region where we call them cyclic supercells, where at some time there's actually two tornadoes on the ground at one time. One is dying off while the other one is basically taking over and newly formed. Okay, so frame by frame, we're going to kind of talk about what it looked like on radar versus what it looked like visually when Will was taking the video frame. So this was at 5:31 p.m. Not a well-defined hook. You can kind of imagine it here on the far left. But if you match it up, you can kind of see some good velocities coming. This is taken from the Granger radar. So this is the green and the blue, the cool colors coming toward the radar. And then a very small area of kind of wind velocities going away from the radar. That is the circulation. So the tornado was technically already on the ground here. On the actual visual, it is hard to see. If you use your imagination, there is probably not a funnel here, but a lot of this dust that you see, which you may kind of confuse with maybe rain, I think this is actually dust being pulled up by the actual tornado, because we do know that the tornado was on the ground at this point. But just visually, it's not very impressive. So as it was crossing the Bell County line at the same moment, again, not a well-defined funnel. The tornado is on the ground here. There is a debris signature down here and on radar, but there's a very good blue and red couplet that we're seeing right on the county line. And again, hook-wise or reflectivity-wise, kind of messy looking. Not ideal, not textbook by any means. But again, it just kind of goes to show you that, you know, the tornado doesn't have to look like a textbook all the time. In this case, it's very hard to tell that there was an actual tornado on the ground, unless you were probably very, very close to it, and you could have seen the circulation, you could see everything kind of being blown around. This is a couple minutes later. We are now getting a well-formed funnel to at least be visible. Again, this is now on the ground. The funnel is not all the way on the ground. Again, in our basic class, we talked about that. The key of spotting a tornado and reporting a tornado is looking for debris at the ground level. This now is kind of saying a hook, and even kind of, I'm not going to really call this a debris ball, but it kind of looks in that realm, and that what we're seeing here, yes, it could be a little bit of rain, but it could also be just a lot of dust and particles being blown up and being sucked up off the ground here. A little bit of a better sort of hook starting to form. We're several minutes later. We're now at 6 p.m. Now we're getting a well-formed funnel. This is now looking a little bit more like a very large sort of tornado with a very large debris cloud being sucked up into the actual tornado itself. 5:39 p.m. A very well-defined hook now on the far left. A very good what we call gate-to-gate velocity couplet, where we have the velocities coming toward the radar, and now this red core going away from the radar. Right where they were meeting up is the tornado on the ground, right basically where I have the cursor right now. Visually, again, kind of went backwards a little bit compared to maybe a couple of minutes ago, but you can still see that there is definitely something on the ground. And of course, this is video too. This is a screen capture of video. Video, you'd be able to see the rotation and everything else kind of happening with it. A well-defined hook, a well-defined couplet on radar, yet you can barely see a little bit of a funnel there, but yet there's a very, very large tornado on the ground here. So again, not a great funnel type of view of a tornado, but that will actually change here in a couple of segments. Beautiful hook, great couplet, and here again you see the tornado. Now it's even better. This is probably, we're getting close to its peak as far as its intensity and everything else. The colors on our velocities are much deeper. The rotation and the actual hook is much better, and the representation on the actual image is much better as well. Getting stronger, probably well into that EF3 range right now. This bowling ball looking of a hook. Really, really tight couplet of velocities. These are kind of what we consider no-brainers as far as tornadoes on the ground, just from all the different evidence that we're getting on radar. And the visual, of course, is very impressive, a very large tornado on the ground at 546. 2 minutes later, can you even see it now? This one is getting a lot of rain now basically wrapped around it. You can see this expansion of reflectivity around it is just a lot of rain now also. So velocity-wise, it's even better, but yet visually, it just looks like a massive rain-wrapped kind of tornado. Again, if you were there and watching video and seeing it in person, you would hopefully maybe be able to see a little bit of rotation in there, but just from a still image, it looks like a big rain shaft at this point. Still very, very good on velocities, a little bit messier now on the actual reflectivity, but visually still a large tornado. This is kind of now a speed up of the entire video. So in fact, you can see the spinning that is actually happening even when the velocity or the funnel was kind of gone. And here's where it's a very, very large tornado. Again, a lot of rain starting to wrap around it. You can see some sunlight kind of coming through, and that was kind of at its dissipating stage. A lot of times what'll happen, the rear flank downdraft will come through and kind of help to dissipate it like that. These were some of the images that were totally devastation. The trees, when I was talking about it, looked like a bomb went off. All these trees, this was a very heavy forested sort of area with oaks and everything, and it was sad. All of that was just all knocked down and shredded, and it was like I said, the most impressive type of tornado damage that I've seen in my 30-year career. So I've been lucky enough not to have to work an EF4 or an EF5 tornado before, but this was it was scary when you kind of saw what the after effects were, and to